LeChatelier's principle helps us understand what chemical systems do when they're stressed or disturbed. If a chemical system is at equilibrium, so once a system reaches equilibrium, if you disturb or stress it, here's what it says: the system will react in the direction that counteracts the disturbance and or relieves the stress. So, kind of like people, when people are stressed or disturbed, we tend to react in a way that's going to counteract our disturbance or relieve the stress. And that's also how reactions respond. So we might think about, well, what disturbs reactions or stresses them? Well, adding and removing reaction components stresses a reaction. And what is a reaction component? It can be a reactant, a product, heat, so temperature. Those things are all changing the pressure. All of these things are reaction components. So adding and removing a reaction component is a stress. So let's see how a reaction responds when we change some of these things. So let me write them down. So things like concentration, that's a reaction component. Temperature, reaction component. Pressure. These are the three that we're going to investigate. These are all components of a reaction that when we add and remove them or change them, causes stress or disturbance to a system. So let's look at what would happen. So first, we're going to categorize it. How does it respond when you add a reaction component? And in this case, we're talking about changing the concentration or temperature. And you can see here when you add, it will shift to the opposite side. So you may think, well, what are we talking about sides? Well, remember, we have two sides of a reaction. We have the reactant side and the product side. So reactants are on the left and products are on the right. So if we add a component to the left, it would go to the opposite side, which is the right. If we add something to the right, it's going to go to the opposite side, which is the left. So adding concentration or temperature will make it go to the opposite side. So let's say if I add something that's on the reactant side, it's going to, what we call, this is how you say it, shift right, because reactants are on the left, so it goes to the opposite side. If, I'm going to write it up here, we add a product, which is on the right, it's going to shift to the opposite side, and we say shift left. And when we talk about shifting, so when we shift right, which would be toward the product side, what we're saying is the reaction responds by making more products. If we shift left, then the reaction is responding by making more reactants. Okay, so adding causes us to shift to the opposite side. Well, what about removing? And so in this case, we're removing a reactant or product and removing a temperature. And you can see right here, when you remove, it shifts to the same side. So if I remove a reactant from a reaction, it's going to basically make more reactants. So we say it shifts left because the reactants are on the left. It goes to the same side. Reactants are on the left, so if we remove them, it shifts left. Now, if we remove a product, Then products are on the right. So it would go to the same side and it would shift right. So again, think about it. You're removing a product, and so how the reaction responds is by making more product or shifting right. Now for changes in temperature, it's very helpful. This is something that's very helpful to remember because we can treat temperature just like any other reaction component. You see, I included temperature in both of these. If you remember that when you are an endothermic reaction, heat is a reactant. We can include it right with the reactants because endothermic means heat is required for the reaction, so it's a reactant. And if you're exothermic, you're releasing heat, so heat is considered a product. So we can consider heat simply like a product. So you'll need to remember, and we're going to do an example in just a minute. You need to remember, though, that when we'll find out, they'll tell us if a reaction is endothermic or exothermic. And that's letting us know if it's endothermic, we're going to treat the heat as a reactant. And if it's exothermic, we're going to treat heat as a product. And here I just wrote what I wrote on the other side. Now for me, pressure is the weirdest one. Remember I said there's concentration, check, temperature, check, and then there's pressure. And here's pressure. And I really have to think about this one when I'm doing the pressure problems. I really do. So here it says if you increase the pressure, it shifts to the side with fewer moles. And if you decrease the pressure, it shifts to the side with more moles. Now, this is not a calculation. When we're dealing with reactions that have gases, we can use the coefficients as to help us figure out the number of moles. So for example, I'm going to write an equation, and these are all in the gaseous state. These are all gases. I just don't have very much space here to write the G. So here's a reaction, and these are all gases. And so how we figure out which side has more moles and fewer moles is by the coefficients and adding them. So here's a 1 and here's a 3. So on the reactant side, I have 1 plus 3. So I have 4 moles. Then on the product side, there's only one thing. So that's just a 2. So I have 2 moles. So this side would have more moles, and this side has fewer moles. So rereading the definition, if I increase pressure, it would shift to the side with fewer moles. So if I increase pressure, this would be the side that it would go to. And then if you decrease pressure, it shifts to the side with more moles. So if I decrease pressure, then it would shift to the left or to the reactant side. So again, we're using coefficients to figure out the number of moles. So I have 2 problems, and you may need to print out these notes and look at them while we do this, but I'll try to guide you through how we would think about it. So this says it's an endothermic reaction. So right away when I see endothermic, I remember that heat is required. So heat is a reactant because heat is required. So they tell me this, and so I just put plus heat. I just write it right onto my paper. Now, what I know with reaction components like temperature and concentration is if I add, it shifts to the opposite side. And if I remove, it shifts to the same side. Okay, this is my left on my reactants, and this is my right on my products. So I decrease O3, and remember the brackets mean concentration. So here's O3. So you decrease, you remove, it goes to the same side, so that means O3 is on the right, it's going to go to the right. Let me erase what oops, I don't want to erase that. Okay. Oh. I was trying to make it so I didn't get too much writing, but I think I'm going to have to do this. So let me go. This is a 2. All right. I'll just do different colors. How about that? So here I decrease, which means remove. So that means it's going to go to the same side. So I look for O2. Here's O2. It's on the left, so it's going to go on the same side. So this goes to the left. Increase. Now, when you increase, you're adding, and so it's going to go to the opposite side. So I find O3. O3 is here. It's on the right. So the opposite side would be to go this way to the left. So this would be to the left. And I'm just writing R for shifting. So this is shift right. And L I'm writing for shift left. And remember, when you shift right, that's a product side. So that just means you're making more products. That's how it's responding, because that's what we're trying to predict. And if you shift left, it means that it's responding by making more reactants. Now, temperature can also be treated like a reaction component. And I'm decreasing temperature, and when I decrease, it's removing, so it's going to go to the same side. Now, this is where endothermic comes in, and so I see the heat is over here on the left. And so if I'm removing it, it goes to the same side, so then this would shift to the left. Now, I haven't talked about a catalyst, and if you recall from the energy diagrams, a catalyst is just a helper. It's not a reactant or a product. It doesn't get used up in the reaction. And a catalyst makes what its job is, it makes the reaction go faster. But a catalyst, we're talking about equilibrium here. And a catalyst doesn't change the equilibrium because it makes it go faster forward and in the reverse. So this actually has no effect on the equilibrium. So it does not cause it to shift left or right. And then finally, the pressure. So if we remember with pressure, and I'm going to go back so you can see it's a little different. It's down here. And pressure has to do with the number of moles. And the moles we get from the coefficients. So if we increase the pressure, it goes to the fewer. Decrease, we go to the more moles. So I'm going to write it down here. Increase, we'll go to the side with fewer. Decrease, we'll go to the side with more. And how we figure it out is the coefficients. So this side, the left, has a 3. And I'm just going to write left has 3 moles down here. The right side has a 2. So what am I doing? I'm increasing pressure. So it's going to go to the side with fewer moles. And that is the right side. So this is going to shift right. So let's try another one, and you can always pause this before I get answering, but you can always pause. So I see this is exothermic, so exothermic releases heat. And so I remember from the first page, when we release heat, we can think of heat as a product. So I just write it over there, plus heat. Now when we're adding and taking away reaction components, if we add, it goes to the opposite side. And if we remove, it goes to the same side. So I'm going to do it in different colors here so we can see. So I see decrease the concentration of HI. So I find HI is over here. And I'm going to write up here left and right. That means the left side and the right side. So decrease means remove, so it goes to the same side. So if I'm removing HI, it's going to go to the right side because it's going to, and remember, this is really, I'm just abbreviating, this is shift right, which means it's going to make more products. Now I can go to this one, increase, which means add. It's going to go to the opposite. And this time it's the concentration of H2. So H2 is on the left side, so it's going to go to the opposite, which would be to the right side. Decrease, which means remove. It's going to go on the same side. I find I2, which is right here on the left, the reactants. So it's going to go to the same side since I'm removing it, so it's going to go to the left. Temperature, so increase temperature. Increase is adding. It's going to go to the opposite side. I wrote it's exothermic, so heat is a product. So going to the opposite side means it's going to the left, and this is going to go to the left. Now, I always like a catalyst because catalysts do not affect equilibrium. Instead, they affect how fast a reaction goes. So this adding a catalyst will have no effect on the equilibrium because it affects the rate of both the forward and the reverse reaction. And now finally, pressure, which remember has different rules. So if we add, it goes to the side with fewer moles. If we remove pressure, decrease it, it goes to the side with more moles, and we're increasing pressure. So we look, this side has a 1 and a 1. So the reactant side, sorry, I don't know why I put R, I meant left. I was thinking reactant. The left side has 2 moles, and the right side has, the product side also has 2 moles. So they're the same. So when you have the same number of moles on both sides, changes in pressure will not have an effect on your reaction. So review the rules, thinking again in general terms. Remember, left, L, means reactants, right, R, means products. Shifting one way or the other is a response of the reaction to disturbances. And if you shift to the left, you make more reactants to respond. If you shift to the right, you make more products. Eventually, with changing the reaction concentrations, the equilibrium will return. If you change, and the equilibrium constant will be the same. If you change the temperature, though, the equilibrium constant is temperature dependent, so an equilibrium will return, but the equilibrium constant would not be the same.